Imagine descending into a world entirely devoid of sunlight. The temperature drops to near freezing, and the water pressing in from all sides carries enough weight to crush solid titanium. This environment exists inside a massive, crescent-shaped scar torn into the floor of the western Pacific Ocean. This topological map of the Pacific seafloor outlines the Mariana Trench. Deep within this structure lies a specific depression called the Challenger Deep, measured as the absolute lowest point on Earth's surface. This physical environment remains the most inaccessible frontier on our own planet. To grasp the true scale of this abyss, we look to humanity's standard reference for extreme elevation, Mount Everest. This chart conceptually inverts Mount Everest, dropping it into the Challenger Deep. Even with Earth's highest peak completely swallowed, a massive void remains. Everest's summit would sit buried under more than a mile of dark water. The sheer volume of this physical space demonstrates how deeply insulated this environment is from the sunlit surface we inhabit. Plunging into the trench requires navigating a rapid loss of solar energy. The bright blue surface water quickly fades into twilight, eventually giving way to absolute blackness. Stripped of all solar heat, the ambient temperature stabilizes just a few degrees above freezing. But the primary danger is hydrostatic pressure. With every meter of descent, the sheer weight of the water column pushing down increases exponentially. This graphic visualizes the immense downward force at the floor of the trench. The hydrostatic pressure here is equivalent to the mass of 50 commercial jumbo jets stacked directly onto a single person. These physical extremes create a hostile environment that, by standard biological rules, should not sustain life. Creatures in these depths create their own chemical light, a process called bioluminescence, to hunt and communicate in the void. Because plants cannot undergo photosynthesis without sunlight, this deep-water ecosystem requires an alternative source of calories. The answer falls from above. A continuous shower of organic debris, known as marine snow, drifts down from the sunlit upper layers of the ocean. The majority of the organisms in the deep ocean survive by scavenging these biological scraps as they settle onto the seafloor. Further down, the geology of the seafloor shifts. Chimney-like rock formations rise from the crust, spewing superheated, mineral-rich fluids directly into the freezing water. These structures are hydrothermal vents, powered by geothermal energy radiating from beneath the Earth's crust. They support a biological process called chemosynthesis. Specialized bacteria absorb the toxic chemicals venting from the Earth and convert them into life-sustaining energy. This energy base supports specialized ecosystems. Dense colonies of massive tube worms and blind crabs cluster around the heat of the vents, thriving completely cut off from the sun. Chemosynthesis proves that biology doesn't require a star to flourish. It only requires an energy gradient. This biological reality forces us to look beyond our own planet, identifying other worlds where lightless oceans might exist. Jupiter's moon Europa is a primary candidate. Observations indicate it conceals a liquid ocean trapped beneath miles of thick surface ice. Saturn's moon Enceladus presents a similar profile. Telescopes have captured plumes ejecting from its southern pole, suggesting active hydrothermal processes below its frozen crust. While chemosynthesis is an established fact on the Earth's seafloor, scientists hypothesize that similar hydrothermal vents could power life inside Europa and Enceladus. Studying the Mariana Trench provides a working model for these environments. It acts as a real-world simulator for the conditions necessary to sustain extraterrestrial life. While telescopes map distant moons, exploration of our own deep ocean remains limited. Large portions of the seafloor have never been directly observed. Challenger Deep demonstrates how life adapts to survive under freezing cold, total darkness, and crushing weight. The biological survival mechanisms found in the deepest shadows of Earth provide the primary data for understanding how life might exist elsewhere in the universe. Would you dare to explore the mysterious, dark depths of the Challenger Deep? Subscribe to FactNest for more science stories.